Okay, so we're going to talk about MO theory, and this is generally the time in the semester when students start to appreciate the power and simplicity of resonance structures. In other words, this is going to be clunky and hard to work with. It does, however, offer an alternative strategy because Lewis structures have fundamentally the problem where they break down. Lewis structures break down when you have to deal with extended pi systems, when you have to deal with multiple p orbitals in a row and some electrons that are going to populate those. So this is an alternative strategy. Having said that, before we can get into the MO theory for these two molecules, I really should revisit the resonance picture. So we're going to generate the resonance picture here. You should be able to generate these and check yourself with the rest of the video. And then in the next video, what I'll do is draw out the MO picture for the molecules instead so that we can compare them. If you're trying to generate a resonance structure for allyl cation, then it's pretty clear that the only way that you can spread this plus around into a better place is to take electron density for the nearby double bond and simply add it into creating a double bond there. That will then, of course, leave behind an area where the double bond used to be, and now because it only has two hydrogens at this position, you have a plus charge resulting at that spot. Of course, if you are interested in going back the way you came, you simply take this pair of electrons in the double bond and shift it back over. And so resonance then will arrive at a picture whereby both molecules do not describe fundamentally the way the molecule looks. Neither picture is correct in and of itself, but instead what you have is the superposition of both. In other words, the blue picture isn't correct, the red picture isn't correct, they're both resonance contributors, but the actual resonance hybrid in the way the molecule behaves is something rather more like this. This is of course not a valid Lewis structure. It is, however, the weighted average of both Lewis structures. This is more what the molecule looks like. And again, fundamentally what we're doing is generating two different Lewis structures to try to represent the same molecule, because Lewis structures break down when you have extended pi systems. The exact same analysis can be done for this acetate ion as well. The only difference is that here the lone pair from the oxygen is going to kick things off. Essentially we need two arrows to generate the resonance structure, whereas here we only needed one. So the lone pair creates a double bond that creates too many bonds to this carbon in the middle, so the double bond then becomes a lone pair on this oxygen, which had two lone pairs originally. And so the new form that we're going to end up drawing will now contain a oxygen with three lone pairs and a minus charge on top, as well as now a double bond to the oxygen that's bottom right, and it now has two lone pairs. Once again, I have drawn two resonance contributors here, and neither one of them is fundamentally correct, but instead there needs to be a resonance hybrid. However, if I wish to go back from red to blue, what I would do is take this lone pair, create a double bond, which of course forces this double bond to become a lone pair on that oxygen, and that's how you return to the blue structure. The true resonance hybrid for this molecule then would be partial double bond character to both oxygens, partial minus charge on both oxygens. I'm not specifying the lone pairs because, again, this is fundamentally a different picture. And again, neither Lewis structure is correct, neither resonance contributor is correct. Instead, the molecule does not look like either one. The molecule looks like the weighted average of both. This is the correct answer for this structure.